4 minus plus C2O4 2 minus C2O4 2 minus going to MnO2 plus CO3 2 minus. All right, is this chemical reaction a redox reaction? Do you want to go pick up those slides? There's a couple more slides. This chemical a redox reaction? So this was easy to see because we can just look at atoms and count electrons, right? But we also need to have the ability to look at chemicals like this and identify oxidation numbers of elements within compounds, right? Okay, so let's start with an easy one here. What's the oxidation number of the manganese in this compound? 0? 2? All right. How about this? How about we talk with our neighbors, find some common ground, hey, or do we want to vote? Maybe we just vote on it. Yeah, just vote? I heard 0 and 2 so far. Anybody else?
Vote.
Huh? Vote, okay. 0 and 2. Anybody, any other choices? 4. Anybody else want to vote for something? You're going to vote for 4? Okay, who votes for 0? Raise your hand. Who votes for 2? Raise your hand. 1. Wait.
I changed my answer.
3 people voted for 2. Who votes for 4? Okay. So 4 wins. That'd be a fun game, huh? Medicine by vote, right? The patients decide what they should do. You should do surgery on me. You should just give me some vitamins. Okay. So the answer is 4, right? Because there's 2 oxygens, and each oxygen has what kind of a oxidation number? -2. And that contributes a -4 to the whole compound. And what should I'm going to erase this now. What should the whole or the sum of all the oxidation numbers be for this compound? 0, right? And the sum of the oxidation number adds up to whatever the charge is. That's one of our rules on slide 9, right? Okay. So what does that mean manganese is here? +4. Another way we could have thought about it is this is an ionic compound called manganese 4 oxide. And the charge on the manganese is the oxidation number or the charge on a singular atomic atom is the charge on the is the oxidation number on that element in an ionic compound. All right, so manganese here is a +4, and oxygen's a -2. We can have those up there. How about over here? What's the manganese oxidation number over here? 8. There's one vote for 8. Any other numbers? 4. The oxidation number on the manganese here. What's that? Did you say something? 9? Are we guessing now?
Wait.
Did somebody say something else? 7? Did I hear 7?
7.
Okay, let's vote. Let's vote. Who votes for 8? One person. Who votes for 4? 1, 2, 3, 4 people. Who votes for 9? One person. Who votes for 7? One person. Oh, man. 7 is the answer. Very good. 7's the answer.
Wait, why is it 7?
Yeah, I know. I wish there was rules instead of just everybody voting and finding out what the thing is. So the list of rules is on slide 7, right? What rules apply to this compound here? The sum of all the oxidation numbers, so the sum of all the manganese plus the sum of all the oxygens equals -1. Is that one rule? Okay. Is that like the last rule? Or is that on slide 8? Or 10? Slide 10. What's that? It's the last rule on slide 9? What's it say? Could somebody read that one for me?
The sum of all oxidation numbers of the atoms in a molecular polyatomic ion must equal the charge on the particle.
Okay.
So is oxygen a particle?
No, this whole thing, the MnO4 is our thing, right? And there's a -1 charge on it. So the sum of the manganese plus the sum of the oxygens equals -1. Okay, so what is the rule for oxygens? -2. And because there's 4, that means all the oxygens are contributing a -8. So what does the manganese have to be? A +7. Right? Anybody want to talk more about that? Okay, so manganese is a +7. So, is this a redox reaction? Manganese went from a +7 over here to a +4 over here. So it is a redox reaction, isn't it? Was manganese oxidized or reduced? Reduced. The number +7 went all the way, it was reduced all the way down to +4 by gaining how many electrons? 3. 3 electrons. Okay, very good. Now, I'd like you guys to find out how many electrons, and if this one was, I mean, what do you think? Was this going to be oxidized or reduced, this species? Probably oxidized, right? I mean, not probably. It has to be if we're doing things correctly. So find out which species was oxidized, the carbon or the oxygen. Find out the oxidation number. How many electrons? Okay? Go for it. What's the oxidation number of the carbon in those compounds or those polyatomic ions? If you're stuck, you can raise your hand. You can try your neighbor power, see how that's working out today.
Here's the extra slides.
Oh, okay, great. Okay, what do you think? C as in cat? Oh, you mean carbon? What's the oxidation number on the left here? Did anybody get it? 6?
Wait.
What?
+6 +8.
Oh, okay. So the contribution by the carbon is 6, you're saying?
Yeah.
Because this brought a -8, and the sum has to be a -2. Okay, so each of the carbons then is what? A +3. Very good. So that carbon is a +3. Anybody want to talk about how we knew that? No? Everybody's gotten, because everybody's going to have to be able to do this sort of thing. All right. All right. So we look at the rules on slide 9. The rules for the elements in this kind of compound says that oxygen is a -2. There's 4 of those. That's the sum of a -8. So the -8 plus whatever the carbon is contributing has to equal a -2. And so that's how we know that the carbon must be here, a +6. But there's 2 carbons that are contributing that +6. So each carbon is a +3. And that's all we're interested in, is what the individual atoms are, not the collection of all the atoms, right? So if we wanted to say the oxidation numbers for the elements in this compound, carbon is a +3, oxygen is a -2. Okay, how about this one over here? +2. Oxygen's a -3 times 2, a total of -6. So something plus the -6 has to equal a -2. So it's a +4. Thank goodness, because if it was a +2, it would have been reduced as well. And that would be, you know what that's called? A mess, right? Yeah. Okay, so this is a +4. So it took 1 electron, this species gives up 1 electron to form that species, right? Okay, so it is a redox reaction. So we need to be able to look at the oxidation numbers on the elements within a compound. We're not just going to be given simple ones, right? We need to be able to look at the elements within a compound and determine whether it's a redox reaction or not. Now, I'm going to teach you to balance a redox reaction after you know that it's a redox reaction, right? Now, let's look back at our little example here that we had, where we had a silver ion. I think I actually had a silver atom on this side. And an iron, silver atom, iron, ion, going to a silver ion and an iron atom. Okay? According to how I've taught you so far to balance reactions, with what you understand about balancing reactions, you would have to look at this and say, okay, that reaction is balanced. There's one silver over here, one silver over here, one iron over here, one iron over here. Right? But maybe you're already seeing that that's not necessarily the case, or that this reaction does not make any sense. Because silver is doing what in this process? It's becoming oxidized. How many electrons is it losing? 1. Whereas iron is becoming, whoops, sorry about that. Iron is becoming reduced, and it's gaining what? 3 electrons. Where is it getting those 3 electrons if silver is only losing 1? What's that? Yeah. So to balance this reaction, you need to have a 3 there. Okay? Now that's all fine and dandy if you can kind of visualize easily. But when you get something like this, it becomes pretty complex. Difficult to see exactly how we're going to be able to balance a redox reaction like this. Okay? So we're going to teach you a method to balance a redox reaction, and the method essentially takes into account the electrons in the compound as well. And the method might seem like, oh, that's so hard, but it's really quite relieving because it allows you to know step by step what to do. Whereas before, you guess and check, go back and forth until you'll finally get there, but it takes a long time. This way, you know within like 5 steps, you're going to have the equation balanced. All right? So these steps are on slide 15. Slide 15. All right, the steps to follow. And we're going to use this example here to follow those steps. The first step is to split the reaction into half reactions. Half reactions. Now, I just mentioned that you can't call a reaction a reduction reaction, or you can't call a reaction an oxidation reaction. You have to call it oxidation, reduction, reduction, oxidation, or a redox, right? But you can call a half reaction a reduction reaction, or a half reaction an oxidation reaction. Because what did we say is this species is doing in this process? It's being reduced. And so I can just write a half reaction minus going to MnO2. Say there is my reductive half reaction. So this is the reduction part of the half reaction. All right? Because it's hard to see behind the podium here, I'm going to write the other half reaction over here. What's the other half reaction? C2O42 minus going to the carbonate ion, right? There's the other half reaction. This is my what? Not my reductive, but my oxidative half reaction. Okay? So that's the first step. Separate your redox reaction into half reactions. The next step is you balance everything that's not oxygen or hydrogen by changing coefficients. All right? So everything that's not oxygen and hydrogen. What's left? Just the manganese. Is it balanced? It is balanced. So there's nothing left to do. Over here, everything that's not oxygen and hydrogen. Carbon, is there anything I need to do to balance them? Yeah, I need to put a 2 right here. All right, that's the first step, or second step. Balance everything that's not carbon and hydrogen. The next step is to balance oxygens. We balance oxygens by adding water molecules. So it's really easy. You just have to count up how many oxygens you need on the side you need it and add water molecules. Let's do this one first. Which side needs more oxygen, the left or the right? The right. How many more oxygens does it need? 2. So I'm going to add 2 what? What did I say? 2 water molecules, right? And what that does for me is it balances my oxygens. How about over here? Which side needs more oxygens? The right side has how many? 6. How many does the left side have? 4. So it looks like I need how many on the left? 2 more oxygen, whoops, H2Os, 2 more water molecules. Did everybody follow that? Why am I adding water molecules? To balance what? The oxygen. Okay, the next step, to balance hydrogens, I add hydrogen ions. Hydrogen ions. All right? So, which side needs more hydrogen in this half reaction? The left. How many do I need? 4. So I'm going to add 4 hydrogen ions. Right? So we minimize the thinking. We just add water molecules for oxygen, hydrogen ions for hydrogens. How about this side? Which side needs more hydrogen ions? Right? How many? 4. 4 H plus ions. Okay? To finish balancing these half reactions, the last thing I need to do is, or I should say finish prepping them, the last thing I need to do is balance the charge with electrons. Okay? So what I do is I look at the molecules that are charged. See this one? The hydrogen ion has a plus charge. This one, the permanganate ion, has a minus charge. Right? So what's the sum of all the charges here? I got 4 pluses and 1 minus. So that's a total of what? Plus 3. Can everybody see how I got that? Anybody want to talk about how I got a plus 3 there? So what I did was, I saw that this was a plus charge, hydrogen ion, and I had 4 of them.
Oh, okay.
And this was a negative charge, and there's just 1 of them. So it's a total of plus 3. What's the sum of the charges on the right side here? Anything charged? No. There's a pretend 0 here and a pretend 0 there, right? No charges. So the right side is uncharged. When I add electrons, it's like this. An electron, each electron has a negative charge. So I'm going to use that to balance the more positive side with whatever the other side is here. So I'm going to add 3 electrons here. Now if I add up this charge, it's not going to be plus 3, but it's going to be what? 0. And that one is ready. It's prepped and almost ready to go. Okay, so which side needs more negative charge in this half reaction? What's the sum of the charges on the left? Minus 2. What's the sum of the charges on the right? Minus.
Oh, minus 2. No, 2.
Plus 2?
Oh, wait. 0.
0? Does everybody agree with that? Anybody want to talk about how we got 0? Raise your hand if you want to talk about it. Okay, so which side do my electrons need to go on? Yeah, the more positive side, which is the 0. And how many do I need to add? 2 electrons. All right, so now the sum of the charge over here is the minus 2, same as this one. Okay. So with those 2 balanced half reactions here, I now combine them together. I combine them together, add them together. Everything that's on the reactant side sums together. Everything that's on the products side sums together. But before I add them, I want to make sure that by adding them, the electrons will be canceled out on both sides. So I have to have the same number of electrons on the reactant side as I have on the product side. How am I going to do that? What am I going to have to do so that when I add these 2 together, the number of electrons drops out? Remember, like with the silver ion, I had to have 3 times as many silver ions as iron ions so that each silver was giving up 1, right? So what am I going to have to do here? I'm going to have to multiply the top one by 2 and the bottom one by 3 so that the number of electrons will cancel out, right? Because I have 3 electrons in my top one and 2 on my bottom one, and the least common multiple there is 6. So, here we go. I'm going to write down the whole reaction now. starting on the reactants side, I can start right here. What do I have to multiply this one by? 3. And this one by 2, right? Okay, so how many water molecules are going to be contributed by this part of the reaction? 6. Does everybody see that? Plus what? 3 of these carboxylate ions. Everybody see where I'm getting these values? Now I'm going to pick up these reactants over here. How many electrons? 6 electrons. H plus ions. Plus 8 H plus ions. 2 of these permanganate ions, MnO4 minus. Okay, product side, starting right here. 6 carbonate ions, CO3 2 minus. 12 H pluses. 6 electrons. How many of these? How many manganese 4 oxides? 2. 2 of these MnO2s plus what's left? 4 waters. Okay, now all I have to do is cross out anything that's the same on both sides. So like the electrons should cross out. The water molecules, how many do I have here? 6 and 4. So I'm going to end up with how many on the left? 2 water molecules over here. Okay? Hydrogen ions. Looks like these are going to cross out, and I'm going to end up with 4 H pluses over here. Okay? So the resulting balanced half reaction is going to be this, right? Which should be what I have here. 2 water molecules, 2 water molecules, 3 of these, 3 carboxylate ions, 2 of these, 2 permanganate ions, 6 of those, 4 of those, and 2 of those, right? Okay? Does everybody see how that works? Should we try one? Or we'll go nice and slow so that there's... Does anybody need to copy anything else down here? Okay? We'll go nice and slow so that... Make sure we know what's going on. What's the first step? Separate them into half reactions. Very good. Go for it. Everybody separate these 2 into half reactions. You got the half reactions? That's pretty straightforward, right? Anybody want to talk about how we know what the half reactions are? What do you get? You got manganese going to manganese oxide, manganese 4 oxide, and we got copper ions going to metallic copper. Those 2 half reactions, right? Excellent. So let's focus on to this one first, the manganese going to manganese oxide. Can anybody tell me if this is the oxidative half reaction or the reductive half reaction? Oxidative? What's the oxidation number of the manganese on the left? 0. What's the oxidation number of the manganese on the right? What? Did I hear a number? 4. Well, we're not guessing, right? We know, right? Because there's 2 oxygens. Is everybody clear on that? This is 0. It's metallic all by itself. This is 4 because it's manganese 4 oxide. It's an ionic compound. Another way of thinking of it, 2 oxygens minus 2 each. Manganese has a plus 4. So this is the oxidative half reaction. Good. Okay, so what was the next step after we identify the half reactions? Everything but oxygen and hydrogen. Is the manganese balanced? Yep, that's done. What's next? By adding water. Who needs water? Who needs oxygen? Left or right? Isn't it the right side? Oh, no, sorry, left. Left side, you're right. Left side. Left side needs more oxygen. How many do we need? 2. So we had 2 water molecules, right? 2 water molecules. Okay, now what do we do? Add more hydrogens, or balance the hydrogens by adding protons. Which side? Right side, how many? 4. 4 protons. Very good. Now we have to balance the charge by adding electrons. So hopefully you're not copying down every single row. Hopefully you can just kind of add on each row to the one before. Give yourself some space, just to save yourself some carpal tunnels.
Why is it 4 hydrogen?
Why is it 4 hydrogen? Because we needed to get 4 on the right, because we have 4 on the left. What's the sum of the charges on the left now? 0. What's the sum of the charges on the right? Plus 4? Is that what I heard? No? Yeah? So how many electrons do we need? 4 on the what side? Right side. So we had 4 electrons, and there is one of our half reactions that's balanced, right? Any questions about that? Okay, the next one. This is going to be easy, right? How can I tell it's going to be easy? Because the coppers are balanced. There's no oxygen. There's no hydrogen. All I have to do is do what? Electrons. Where are the electrons going to go? On the more what? Positive or negative side? More positive. So I need how many? 2 on the left side. True? All right. So there is our second half reaction. Now I'm going to combine this half reaction here with this half reaction. But before I do so, I'm going to make sure that what? What am I trying to do when I combine them? The electrons cancel out, right? So how am I going to make that a reality? Yes, 2 of these. So I'm going to have to multiply that one by 2. And then I'm going to add it to this one here. Cross out anything that's extra. I mean, that's the same on both sides. And the result should be our answer. Okay, let's see if you can do it. Add them all together, one whole reaction. Getting it?
Cross out the electrons, yeah.
Yeah, the electrons hopefully have to cancel out, right? If you're adding things together and you see that the electrons are on the same side when you're adding, that's a sign that you made a mistake, right? And you could catch that sign early on when you're balancing the half reactions too, right? Did you get it already? All done? Who wants more time? Raise your hand if you want more time. Okay, 30 more seconds. Right, we're adding these 2 reactions together. This half reaction here, this oxidative one, and this reductive half reaction. We're going to multiply this one by 2 though. Combine them all together. And then we can cancel some things out. It looks like we can cancel some protons out. No? Can we? No, we can't. Just electrons, huh? Just electrons. So that's what's left. Manganese, 2 waters, 2 coppers. Manganese oxide, 4 hydrogens, and 2 coppers. Who got that? Raise your hand if you got that. Okay, good. Anybody want to talk about why they didn't or have any more discussion about this one here?
Why didn't the copper, is it because the electrons are too close?
Why didn't the copper what? Cancel out? Oh, yes, that's right. This is not the same as that. That's right. Good question. Yeah.
So when you're at like the multiplying stage, are you just looking to make sure that the electrons are equal?
That's right. That they're the same on both sides.
Yes.
Because in a redox reaction, there's not going to be electrons. Only in half reactions will you see electrons to help you kind of use as an accounting step to get to your balanced equation. Okay, very good. Now, we also have what we call balancing our redox reactions under basic conditions. Basic conditions. Now, you know what an acid is, right? It's a chemical like this that you put into water, and what does it do? It dissociates, and one of the dissociative products is the hydrogen ion. All right? Now notice in these reactions, in these redox reactions, we're balancing the hydrogens with acid, right? Hydrogen ions with acid. In some cases, you'll be asked to balance redox reactions under what we call basic conditions. This is an acid. A base is a chemical that what? You put it into water, and what happens? The hydroxide ion results. Right? When we're asked to balance a redox reaction under basic conditions, what you do is you balance like we all have been taught, which is under acidic conditions, and then you add to both sides the hydroxide ion, OH minus. You add both sides the hydroxide ion. And you add as many as you have hydrogen ions. So in this case, because we have 4 hydrogen ions, we add 4 hydroxide ions to both sides. What that does is those 4 hydroxide ions are going to combine with those 4 hydrogen ions and form what? What happened? That's right. Form 4 water molecules. Okay? So, after they form 4 water molecules here, 2 water molecules here are going to be able to cancel out with 2 of them here, and you're only going to have 2 left over on the right. You're going to have the 4 hydroxide ions here, and then this bottom one here, is this one, but balanced under basic conditions. See how we converted the balanced equation under acidic conditions to basic conditions by adding the 4 hydroxide to both sides. All right? See that? So, after we're done, if we want it balanced in basic conditions, what do we add to both sides? A hydroxide ion. How much do we add? As many as there are hydrogen ions. Yeah.